Electrostatic potential and capacitance. When an external force does work in taking a body from a point to another against a force like spring force or gravitational force, that work gets stored as potential energy of the body. When the external force is removed, the body moves, gaining kinetic energy and losing an equal amount of potential energy. The sum of kinetic and potential energies is thus conserved. Forces of this kind are called conservative forces. Spring force and gravitational force are examples of conservative forces. Coulomb force between two stationary charges is also a conservative force. This is not surprising, since both have inverse square dependence on distance and differ mainly in the proportionality constants. The masses in the gravitational law are replaced by charges in Coulomb's law. Thus, like the potential energy of a mass in a gravitational field, we can define electrostatic potential energy of a charge in an electrostatic field. Consider an electrostatic field E due to some charge configuration. First, for simplicity, consider the field E due to a charge Q placed at the origin. Now, imagine that we bring a test charge Q from a point R to a point P against a repulsive force on it due to the charge capital Q. This will happen if capital Q and small q are both positive or both negative. For definiteness, let's take capital Q, small q are greater than 0. Two remarks may be made here. First, we assume that the test charge small q is so small that it does not disturb the original configuration, namely the charge capital Q at the origin, or else we keep Q fixed at the origin by some unspecified force. Second, in bringing the charge small q from R to P, we apply an external force F external just enough to counter the repulsive electric force Fe, which means F external equals to minus Fe. This means there is no net force on or acceleration of the charge Q when it is brought from R to P, i.e., it is brought with infinitesimally slow constant speed. Thus, work done by external forces in moving a charge Q from R to P is against electrostatic repulsive force and gets stored as potential energy. At every point in an electric field, a particle with charge Q possesses a certain electrostatic potential energy. This work done increases its potential energy by an amount equal to potential energy difference between points R and P. Thus, potential energy difference delta U is equal to UP minus UR, which is equal to WRP. Note here that this displacement is in an opposite sense to the electric force, and hence work done by electric field is negative, that is minus WRP. Therefore, we can define electric potential energy difference between 2 points as the work required to be done by an external force in moving, without accelerating, charge Q from one point to another for electric field of any arbitrary charge configuration. Two important comments may be made at this stage. The right side of the equation depends only on the initial and final positions of the charge. It means that the work done by an electrostatic field in moving a charge from one point to another depends only on the initial and the final points and is independent of the path taken to go from one point to the other. This is the fundamental characteristic of a conservative force. The concept of the potential energy would not be meaningful if the work depended on the path. The path independence of work done by an electrostatic field can be proved using the Coulomb's law. The equation defines potential energy difference in terms of the physically meaningful quantity work. Clearly, potential energy so defined is undetermined to within an additive constant. What this means is that the actual value of potential energy is not physically significant. It is only the difference of potential energy that is significant. We can always add an arbitrary constant alpha to potential energy at every point, since this will not change the potential energy difference. UP plus alpha minus UR plus alpha is equal to UP minus UR. Put it differently, there is a freedom in choosing the point where potential energy is 0. A convenient choice is to have electrostatic potential energy 0 at infinity. With this choice, if we take the point r at infinity, we get from W infinity P is equal to UP minus U infinity, which is equal to UP. Potential energy of charge Q at a point, in the presence of field due to any charge configuration, is the work done by the external force, equal and opposite to the electric force, in bringing the charge Q from infinity to that point. Electrostatic potential. Consider any general static charge configuration. We define potential energy of a test charge Q in terms of the work done on the charge Q. This work is obviously proportional to Q, since the force at any point is QE, where E is the electric field at that point due to the given charge configuration. It is, therefore, convenient to divide the work by the amount of charge Q, so that the resulting quantity is independent of Q. In other words, work done per unit test charge is characteristic of the electric field associated with the charge configuration. This leads to the idea of electrostatic potential V due to a given charge configuration. We get that work done by external force in bringing a unit positive charge from point R to P is equal to Vp minus V, or which is thereby equal to UP minus U divided by Q, where Vp and V are the electrostatic potentials at P and R, respectively. As before, it is not the actual value of potential, but the potential difference that is physically significant. If, as before, we choose the potential to be 0 at infinity, then it implies that work done by an external force in bringing a unit positive charge from infinity to a point is equal to the electrostatic potential V at that point. In other words, the electrostatic potential V at any point in a region with electrostatic field is the work done in bringing a unit positive charge, without acceleration, from infinity to that point. To obtain the work done per unit test charge, we should take an infinitesimal test charge delta Q, obtain the work done delta W, in bringing it from infinity to the point and determine the ratio delta W is to delta Q. Also, the external force at every point of the path is to be equal and opposite to the electrostatic force on the test charge at that point. Potential due to a point charge. Consider a point charge Q at the origin. For definiteness, take Q to be positive. We wish to determine the potential at any point P with position vector R from the origin. For that, we must calculate the work done in bringing a unit positive test charge from infinity to the point P. For Q greater than 0, the work done against the repulsive force on the test charge is positive. Since work done is independent of the path, we choose a convenient path along the radial direction from infinity to the point P. At some intermediate point P hash on the path, the electrostatic force on a unit positive charge is the factor Q multiplied by 1 Coulomb divided by 4 pi epsilon 0 R squared, the whole multiplied by the unit vector R hash. Work done against this force from R hash to R hash plus delta. R hash is delta W equals to the factor minus Q divided by 4 pi epsilon 0 R squared whole multiplied by the vector delta R hash. The negative sign appears because for delta R hash less than 0, delta W is positive. The factor Q divided by 4 pi epsilon 0 R squared is the potential at the point P due to the charge Q, which is represented by VR. Work done by the external force per unit positive test charge in bringing it from infinity to the point is negative. This is equivalent to saying that work done by the electrostatic force in bringing the unit positive charge from infinity to the point P is positive. So that the electrostatic force and the displacement from infinity to P are in the same direction. Potential due to an electric dipole. An electric dipole consists of two charges Q and minus Q separated by a small distance 2a. Its total charge is 0. It is characterized by a dipole moment vector P whose magnitude is Q into 2a and which points in the direction from minus Q to Q. The electric field of a dipole at a point with position vector R depends not just on the magnitude r, but also on the angle between r and p. Further, the field falls off at large distance, not as 1 divided by r squared, typical of field due to a single charge, but as 1 divided by r cubed. The electric field obeys the superposition principle. Since potential is related to the work done by the field, electrostatic potential also follows the superposition principle. Thus, the potential due to the dipole is the sum of potentials due to the charges q and minus q. The important contrasting features of electric potential of a dipole from that due to a single charge are: 1. The potential due to a dipole depends not just on r, but also on the angle between the position vector r and the dipole moment vector p. It is, however, axially symmetric about p. That is, if you rotate the position vector r about p, keeping q fixed, the points corresponding to p on the cone so generated will have the same potential as at p. 2. The electric dipole potential falls off at large distance as 1 divided by r squared, not as 1 divided by r, characteristic of the potential due to a single charge. Potential due to a system of charges. Consider a system of charges q1, q2, and so on up to qn with position vectors r1, r2, and so on up to rn relative to some origin. The potential V1 at point P due to the charge Q1 is given by V1 is equal to the factor Q1 divided by 4 pi epsilon R1P, where R1P is the distance between Q1 and P. Similarly, the potential V2 at point P due to charge Q2 is given by V2 is equal to the factor Q2 divided by 4 pi epsilon R2P, where R2P is the distance between Q2 and P. By the superposition principle, the potential V at P due to the total charge configuration is the algebraic sum of the potentials due to the individual charges V equals to V1 plus V2 plus, so on up to Vn. If we have a continuous charge distribution characterized by a charge density rho r, we divide it, as before, into small volume elements each of size delta V and carrying a charge rho delta V. We then determine the potential due to each volume element and sum over all such contributions, and thus determine the potential due to the entire distribution. For a uniformly charged spherical shell, the electric field outside the shell is as if the entire charge is concentrated at the center. Thus, the potential outside the shell is given by V is equal to the factor Q divided by 4 pi epsilon r, where r if the vector r is greater than the radius of the shell r. The electric field inside the shell is 0. This implies that potential is constant inside the shell, as no work is done in moving a charge inside the shell, and therefore equals its value at the surface. An equipotential surface is a surface with a constant value of potential at all points on the surface. For a single charge Q, the potential is given by V equals to 1 divided by 4 pi epsilon squared, r, where r is the distance from the charge to the point where the potential is being measured. This shows that V is a constant if r is constant. Thus, equipotential surfaces of a single point charge are concentric spherical surfaces centered at the charge. Now, the electric field lines for a single charge Q are radial lines starting from or ending at the charge, depending on whether Q is positive or negative. Clearly, the electric field at every point is normal to the equipotential surface passing through that point. This is true in general. For any charge configuration, equipotential surface through a point is normal to the electric field at that point. The proof of this statement is simple. If the field were not normal to the equipotential surface, it would have non-zero component along the surface. To move a unit test charge against the direction of the component of the field, work would have to be done. But this is in contradiction to the definition of an equipotential surface. There is no potential difference between any 2 points on the surface, and no work is required to move a test charge on the surface. The electric field must, therefore, be normal to the equipotential surface at every point. For a uniform electric field, E, say, along the x-axis, the equipotential surfaces are planes normal to the x-axis, that is, planes parallel to the yz plane. Relation between field and potential. Consider two closely spaced equipotential surfaces, A and B, with potential values V and V plus delta V, where delta V is the change in V in the direction of the electric field E. Let P be a point on the surface B. Delta L is the perpendicular distance of the surface A from P. Imagine that a unit positive charge is moved along this perpendicular from the surface B to surface A against the electric field. The work done in this process is given by modulus E delta L. This work equals the potential difference VA minus VB. Thus, modulus E delta L equals to A minus V. Substituting VB with V plus delta V, we get modulus E delta L equals to minus delta V. And hence modulus E equals to minus delta V divided by delta L. Since delta V is negative delta V equals to modulus delta V, and we can represent modulus equals to modulus delta V divided by delta L. We thus arrive at two important conclusions concerning the relation between electric field and potential. 1. Electric field is in the direction in which the potential decrease is steepest. 2. Its magnitude is given by the change in the magnitude of potential per unit displacement normal to the equipotential surface at the point. Potential energy of a system of charges. Consider first the simple case of two charges Q1 and Q2 with position vector R1 and R2 relative to some origin. Let us calculate the work done externally in building up this configuration. This means that we consider the charges Q1 and Q2 initially at infinity and determine the work done by an external agency to bring the charges to the given locations. Suppose, first the charge Q1 is brought from infinity to the point R1. There is no external field against which work needs to be done, so work done in bringing Q1 from infinity to R1 is 0. This charge produces a potential in space given by Q1 divided by 4 pi epsilon, R1p, where R1p is the distance of a point P in space from the location of Q1. From the definition of potential, the work done in bringing charge Q2 from infinity to the point R2 is Q2 times the potential at R2 due to Q1. Work done on Q2 is equal to Q1 divided by 4 pi epsilon 0, R12, where R12 is the distance between points 1 and 2. Since electrostatic force is conservative, this work gets stored in the form of potential energy of the system. Thus, the potential energy of a system of two charges Q1 and Q2 is U equals to Q1 divided by 4 pi epsilon 0, R12. Obviously, if Q2 was brought first to its present location and Q1 brought later, the potential energy would still be the same. The potential energy expression is unaltered whatever way the charges are brought to the specified locations, because of path independence of work for electrostatic force. For like charges, where Q1, Q2 is greater than 0, electrostatic force is repulsive and a positive amount of work is needed to be done against this force to bring the charges from infinity to a finite distance apart. For unlike charges where Q1, Q2 is less than 0, the electrostatic force is attractive. In that case, a positive amount of work is needed against this force to take the charges from the given location to infinity. In other words, a negative amount of work is needed for the reverse path from infinity to the present locations, and so the potential energy is negative. Because of the conservative nature of the electrostatic force, or equivalently, the path independence of work done. The final expression for potential energy is independent of the manner in which the configuration is assembled. The potential energy is characteristic of the present state of configuration and not the way the state is achieved. Potential energy of a single charge. Let us explore the question, what is the potential energy of a charge Q in an external field? The external field, E, is not produced by the given charge whose potential energy we wish to calculate. E is produced by sources external to the given charge, that the external sources may be known, but often they are unknown or unspecified. What is specified is the electric field, E, or the electrostatic potential, V, due to the external sources. We assume that the charge Q does not significantly affect the sources producing the external field. This is true if Q is very small, or the external sources are held fixed by other unspecified forces. Even if Q is finite, its influence on the external sources may still be ignored in the situation when very strong sources far away at infinity produce a finite field E in the region of interest. Note again that we are interested in determining the potential energy of a given charge Q and later a system of charges in the external field. We're not interested in the potential energy of the sources producing the external electric field. The external electric field, E, and the corresponding external potential V may vary from point to point. By definition, V at a point P is the work done in bringing a unit positive charge from infinity to the point P. Thus, work done in bringing a charge Q from infinity to the point P in the external field is Q multiplied by V. This work is stored in the form of potential energy of Q. If the point P has position vector R relative to some origin, we can write potential energy of Q at R in an external field is equal to Q multiplied by V, or the term where V, R is the external potential at the point R. Thus, if an electron with charge Q equals E equals 1.6 in a 10 to the power of minus 19 C is accelerated by a potential difference of delta V equal to 1 volt, it would gain energy of Q delta equal to 1.6 multiplied by 10 to the power of minus 19 J. This unit of energy is defined as 1 electron volt or 1 E. That is 1 equals to 1.6 multiplied by 10 to the power of minus 19 J. The units based on EV are most commonly used in atomic, nuclear, and particle physics. Potential energy of a system of two charges in an external field. Let us explore the potential energy of a system of two charges Q1 and Q2 located at R1 and R2, respectively, in an external field. First, we calculate the work done in bringing the charge Q1 from infinity to R1. Work done in this step is Q1 multiplied by VR1. Next, we consider the work done in bringing Q2 to R2. In this step, work is done not only against the external field, E, but also against the field due to Q1. Work done on Q2 against the external field equals to Q2 multiplied by VR2. Work done on Q2 against the field due to Q1 equals to Q1 Q2 divided by 4 pi epsilon 0. R12, where R12 is the distance between Q1 and Q2. By the superposition principle for fields, we add up the work done on Q2 against the two fields E and that due to Q1, and hence the work done in bringing Q2 to R2 is equal to Q2 multiplied by VR2 plus Q1 Q2 divided by 4 pi epsilon 0, R12. Thus, the total potential energy of a system equals to Q1 multiplied by V, R1 plus Q2 multiplied by R2 plus Q1 Q2 divided by 4 pi epsilon 0, R12. Potential energy of a dipole in an external field. Consider a dipole with charges Q1 equal to plus Q and Q2 equal to minus Q placed in a uniform electric field E. In a uniform electric field, the dipole experiences no net force, but experiences a torque τ given by τ equal to P multiplied by E, which will tend to rotate it unless P is parallel or antiparallel to E. Suppose an external torque toe external is applied in such a manner that it just neutralizes this torque and rotates it in the plane of paper from angle theta 0 to angle theta 1 at an infinitesimal angular speed and without angular acceleration. The amount of work done by the external torque will be given by W equals to P multiplied by E into cos theta 0 minus cos theta 1. This work is stored as the potential energy of the system. We can then associate potential energy UQ with an inclination Q of the dipole. Similar to other potential energies, there is a freedom in choosing the angle where the potential energy U is taken to be 0. Considering theta 0 to be pi divided by 2, we get potential energy U equals to minus P multiplied by E. Electrostatics of conductors. Conductors contain mobile charge carriers. In metallic conductors, these charge carriers are electrons. In a metal, the outer valence electrons part away from their atoms and are free to move. These electrons are free within the metal, but not free to leave the metal. The free electrons form a kind of gas. They collide with each other and with the ions and move randomly in different directions. In an external electric field, they drift against the direction of the field. The positive ions made up of the nuclei and the bound electrons remain held in their fixed positions. In electrolytic conductors, the charge carriers are both positive and negative ions, but the situation in this case is more involved. The movement of the charge carriers is affected both by the external electric field as also by the so-called chemical forces. Important results regarding electrostatics of conductors. Inside a conductor, electrostatic field is 0. Consider a conductor neutral or charged. There may also be an external electrostatic field. In a static situation, when there is no current inside or on the surface of the conductor, the electric field is 0 everywhere inside the conductor. This fact can be taken as the defining property of a conductor. A conductor has free electrons. As long as electric field is not 0, the free charge carriers would experience force and drift. In a static situation, the free charges have so distributed themselves that the electric field is 0 everywhere inside. Electrostatic field is 0 inside a conductor. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. If it were not normal to the surface, it would have some non-zero component along the surface. Free charges on the surface of the conductor would then experience force and move. In a static situation, therefore, you should have no tangential component. Thus, electrostatic field at the surface of a charged conductor must be normal to the surface at every point. For a conductor without any surface charge density, field is 0 even at the surface. The interior of a conductor can have no excess charge in the static situation. A neutral conductor has equal amounts of positive and negative charges in every small volume or surface element. When the conductor is charged, the excess charge can reside only on the surface in the static situation. This follows from the Gauss's law. Consider any arbitrary volume element V inside a conductor. On the closed surface S bounding the volume element V, electrostatic field is 0. Thus, the total electric flux through S is 0. Hence, by Gauss's law, there is no net charge enclosed by S. But the surface S can be made as small as you like, i.e., the volume V can be made vanishingly small. This means there is no net charge at any point inside the conductor, and any excess charge must reside at the surface. Electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. Since E equals to 0 inside the conductor and has no tangential component on the surface, no work is done in moving a small test charge within the conductor and on its surface. That is, there is no potential difference between any 2 points inside or on the surface of the conductor. Hence, the result. If the conductor is charged, electric field normal to the surface exists. This means potential will be different for the surface and a point just outside the surface. Electric field at the surface of a charged conductor is given by E equals to sigma divided by epsilon 0 multiplied by n, where sigma is the surface charge density and n is a unit vector normal to the surface in the outward direction. Electrostatic shielding. Consider a conductor with a cavity with no charges inside the cavity. A remarkable result is that the electric field inside the cavity is zero, whatever be the size and shape of the cavity, and whatever be the charge on the conductor and the external fields in which it might be placed. The electric field inside a charged spherical shell is zero. A related result is that even if the conductor is charged or charges are induced on a neutral conductor by an external field, all charges reside only on the outer surface of a conductor with cavity. Whatever be the charge and field configuration outside, any cavity in a conductor remains shielded from outside electric influence. The field inside the cavity is always zero. This is known as electrostatic shielding. The effect can be made use of in protecting sensitive instruments from outside electrical influence. Dielectrics and polarization. Dielectrics are non-conducting substances. In contrast to conductors, they have no or negligible number of charge carriers. When a conductor is placed in an external electric field, the free charge carriers move and charge distribution in the conductor adjusts itself in such a way that the electric field, due to induced charges, opposes the external field within the conductor. This happens until, in the static situation, the two fields cancel each other and the net electrostatic field in the conductor is zero. In a dielectric, this free movement of charges is not possible. It turns out that the external field induces dipole moment by stretching or reorienting molecules of the dielectric. The collective effect of all the molecular dipole moments is net charges on the surface of the dielectric, which produce a field that opposes the external field. Unlike in a conductor, however, the opposing field so induced does not exactly cancel the external field. It only reduces it. The extent of the effect depends on the nature of the dielectric. To understand the effect, we need to look at the charge distribution of a dielectric at the molecular level. The molecules of a substance may be polar or nonpolar. In a nonpolar molecule, the centers of positive and negative charges coincide. The molecules of a substance may be polar or nonpolar. In a nonpolar molecule, the centers of positive and negative charges coincide. The molecule then has no permanent or intrinsic dipole moment. Examples of nonpolar molecules are oxygen and hydrogen molecules which, because of their symmetry, have no dipole moment. On the other hand, a polar molecule is one in which the centers of positive and negative charges are separated, even when there is no external field. Such molecules have a permanent dipole moment. An ionic molecule, such as hydrochloric acid or a molecule of water, are examples of polar molecules. In an external electric field, the positive and negative charges of a nonpolar molecule are displaced in opposite directions. The displacement stops when the external force on the constituent charges of the molecule is balanced by the restoring force due to internal fields in the molecule. The nonpolar molecule thus develops an induced dipole moment. The dielectric is said to be polarized by the external field. We consider only the simple situation when the induced dipole moment is in the direction of the field and is proportional to the field strength. Substances for which this assumption is true are called linear isotropic dielectrics. The induced dipole moments of different molecules add up, giving a net dipole moment of the dielectric in the presence of the external field. A dielectric with polar molecules also develops a net dipole moment in an external field, but for a different reason. The dipole moment per unit volume is called polarization and is denoted by P. For linear isotropic dielectrics, P equals to epsilon 0 multiplied by x, where x is a constant characteristic of the dielectric and is known as the electric susceptibility of the dielectric medium. It is possible to relate Xe to the molecular properties of the substance. How does the polarized dielectric modify the original external field inside it? Let us consider, for simplicity, a rectangular dielectric slab placed in a uniform external field E0 parallel to two of its faces. The field causes a uniform polarization P of the dielectric. Thus, every volume element delta V of the slab has a dipole moment P delta V in the direction of the field. The volume element delta V is macroscopically small but contains a very large number of molecular dipoles. Anywhere inside the dielectric, the volume element delta V has no net charge, though it has net dipole moment. This is because the positive charge of one dipole sits close to the negative charge of the adjacent dipole. However, at the surfaces of the dielectric normal to the electric field, there is evidently a net charge density. The positive ends of the dipoles remain unneutralized at the right surface and the negative ends at the left surface. The unbalanced charges are the induced charges due to the external field. Thus, the polarized dielectric is equivalent to two charged surfaces with induced surface charge densities, say sigma p and minus sigma p. Clearly, the field produced by these surface charges opposes the external field. The total field in the dielectric is, thereby, reduced from the case when no dielectric is present. We should note that the surface charge density plus or minus sigma p arises from bound, not free charges in the dielectric. Capacitors and capacitance. A capacitor is a system of two conductors separated by an insulator. The conductors have charges, say Q1 and Q2, and potentials V1 and V2. Usually, in practice, the two conductors have charges Q and minus Q, with potential difference V equal to V1 minus V2 between them. We shall consider only this kind of charge configuration of the capacitor. Even a single conductor can be used as a capacitor by assuming the other at infinity. The conductors may be so charged by connecting them to the two terminals of a battery. Q is called the charge of the capacitor, though this, in fact, is the charge on one of the conductors. The total charge of the capacitor is 0. The electric field in the region between the conductors is proportional to the charge Q. That is, if the charge on the capacitor is, say, doubled, the electric field will also be doubled at every point. This follows from the direct proportionality between field and charge implied by Coulomb's law and the superposition principle. Now, potential difference V is the work done per unit positive charge in taking a small test charge from the conductor 2 to 1 against the field. Consequently, V is also proportional to Q, and the ratio Q divided by V is a constant. The constant C is called the capacitance of the capacitor. C is independent of Q or V. The capacitance C depends only on the geometrical configuration shape, size, separation of the system of two conductors. The SI unit of capacitance is farad, which is equal to Coulomb divided by volt. For large C, V is small for a given Q. This means a capacitor with large capacitance can hold large amount of charge Q at a relatively small V. This is of practical importance. High potential difference implies strong electric field around the conductors. A strong electric field can ionize the surrounding air and accelerate the charges so produced to the oppositely charged plates, thereby neutralizing the charge on the capacitor plates, at least partly. In other words, the charge of the capacitor leaks away due to the reduction in insulating power of the intervening medium. The maximum electric field that a dielectric medium can withstand without breakdown of its insulating property is called its dielectric strength. For air, it is about 3 multiplied by 10 to the power of 6 V per meter. For a separation between conductors of the order of 1 centimeter or so, this field corresponds to a potential difference of 3 multiplied by 10 to the power of 4 V between the conductors. Thus, for a capacitor to store a large amount of charge without leaking, its capacitance should be high enough so that the potential difference and hence the electric field do not exceed the breakdown limits. Put differently, there is a limit to the amount of charge that can be stored on a given capacitor without significant leaking. In practice, a farad is a very big unit. The most common units are its submultiples like 1 mu F, which is equal to 10 to the power of -6 farad. Besides its use in storing charge, a capacitor is a key element of most AC circuits with important functions. The parallel plate capacitor. A parallel plate capacitor consists of 2 large plane parallel conducting plates separated by a small distance. We first take the intervening medium between the plates to be vacuum. Let it be the area of each plate and d the separation between them. The 2 plates have charges Q and -Q. Since d is much smaller than the linear dimension of the plates, we can use the result on electric field by an infinite plane sheet of uniform surface charge density. Plate 1 has surface charge density sigma equals to Q divided by A, and plate 2 has a surface charge density minus sigma. The electric field in the outer region of the parallel plate is E equals to sigma divided by 2 epsilon 0 minus sigma divided by 2 epsilon 0, which is 0. In the inner region between the plates 1 and 2, the electric fields due to the 2 charged plates add up, giving E equals to Q divided by epsilon 0 multiplied by A. The direction of electric field is from the positive to the negative plate. Thus, the electric field is localized between the 2 plates and is uniform throughout. For plates with finite area, this will not be true near the outer boundaries of the plates. The field lines bend outward at the edges, an effect called fringing of the field. By the same token, sigma will not be strictly uniform on the entire plate. Now for uniform electric field, potential difference is simply the electric field times the distance between the plates, that is, V equals to QD divided by epsilon 0A. The capacitance C of the parallel plate capacitor, which, as expected, depends only on the geometry of the system. Effect of dielectric on capacitance. Let us see how the capacitance of a parallel plate capacitor is modified when a dielectric is present. We have 2 large plates, each of area separated by a distance d. The charge on the plates is plus or minus Q, corresponding to the charge density plus or minus sigma, with sigma equals to Q divided by A. When there is vacuum between the plates, E0 equals to sigma divided by epsilon 0. Consider next a dielectric inserted between the plates, fully occupying the intervening region. The dielectric is polarized by the field, and the effect is equivalent to 2 charged sheets at the surfaces of the dielectric normal to the field, with surface charge densities sigma p and minus sigma p. The dielectric constant of a substance is the factor greater than 1 by which the capacitance increases from its vacuum value, when the dielectric is inserted fully between the plates of a capacitor. Energy stored in a capacitor. To determine the energy stored in a system of 2 conductors, consider initially 2 uncharged conductors 1 and 2. Imagine next a process of transferring charge from conductor 2 to conductor 1 bit by bit, so that at the end, conductor 1 gets charge Q. By charge conservation, conductor 2 has charge minus Q at the end. In transferring positive charge from conductor 2 to conductor 1, work will be done externally, since at any stage conductor 1 is at a higher potential than conductor 2. To calculate the total work done, We first calculate the work done in a small step involving transfer of an infinitesimal amount of charge. Since electrostatic force is conservative, this work is stored in the form of potential energy of the system. When the capacitor discharges, this stored-up energy is released. It is possible to view the potential energy of the capacitor as stored in the electric field between the plates. Energy stored in the capacitor equals to half Q squared divided by C, which can be represented as half A sigma squared multiplied by D divided by epsilon 0A. Note that AD is the volume of the region between the plates, where electric field alone exists. If we define energy density as energy stored per unit volume of space, then the energy density of electric field U equals to half epsilon 0 E squared. The result on energy density of an electric field is very general and holds true for electric field due to any configuration of charges.